Let's go ahead and look at some of these problems. We're asked to find reference angles. So in your homework, you'll have a question that looks something like this. Find the reference angle of a 130-degree angle. Or find the reference angle of a negative 50-degree angle. Or find the reference angle of a 4 pi over 5 angle. Or finally, find the reference angle of a 15 pi over 7 angle. So, let's define what reference angles are. It's not really very difficult. Let me write down what definition I like to use, and then we'll start looking at some of these, and I don't think you'll find it very difficult. So, definition. If you're given an angle, like up here, these are angles we're given. The reference angle is the smallest, or maybe you can think of shortest, angle back to the positive or negative x-axis. All right, that may not be very clear in words, but when I do some of these examples, I think you'll find it pretty simple. Let's just look at this first example. Let's just go draw a 130-degree angle. So hopefully by now you're getting pretty familiar with angles. So if 0 degrees is here, 90 degrees is here, you know, we sort of think of these as the traditional X and Y axis. So let's go draw on here a 150-degree angle. So if 90 is here, I need to go 40 degrees past this. As an estimate, maybe that's a reasonable estimate of a 140-degree angle. The reference angle says, from here, what is the shortest angle or the smallest angle back to the x-axis? Meaning, here's an angle back to the x-axis, or here's an angle back to the x-axis. Well, obviously, this angle is shorter, so this becomes the reference angle. And it's pretty easy to see if it's 140 degrees here, and this is 180, the reference angle is 40 degrees. Now, one thing to make note of, reference angle is always going to be a positive number. Excuse me. Even if you feel like you're moving in a negative direction to find a reference angle, when you finally give the reference angle, it's always a positive number. How about this? We're given a negative 50-degree angle, and we're asked to find the reference angle. So, with reference angles, the best thing to do is to go draw your original angle. So I'll just write it here. A minus 50-degree angle. So remember, negative angles now we go clockwise, so you can think of down here is minus 90 degrees. So minus 50-degree angle might be something like this. So with this angle, you have two choices to get back to the x-axis. You can either go this way to the positive x-axis or this way to the negative x-axis. Well, obviously, this direction is the closest or the shortest. So this is going to be my reference angle, and this distance is 50 degrees. So the reference angle of a negative 50-degree angle is 50 degrees. Let's do a couple problems in radians. Now this gets a little trickier because once again, these angles in radians are usually fractions and we have to deal with fractions. So let's look at first 4 pi over 5. So my angle is 4 pi over 5. And we want to know what the reference angle is. Now what makes this tricky is this denominator of 5, because if I draw, or I mark here my angles in radians, zeros here, pi over 2, pi, 3 pi over 2. First thing I need to do that would be most beneficial is to try and sketch a 4 pi over 5 angle. Well, it's a little tricky because my denominator is 5. Here's what I always do and what I suggest you do. Zero's here, pi is here. I want to rewrite this angle pi and convert it so that it has a denominator of 5. Now I'm going to write it here and hopefully you'll all see that this is pretty obvious. 5 pi over 5 is actually the same as pi. All I've done is now made this into a fraction. So hopefully you can see now, so 4 pi over 5, if you think of a fraction, 4/5 is almost 5/5. So my guess is it's going to be over here someplace. And that is in fact the case. I can probably guess it might be there's a 4 pi over 5 angle. But what I'm asked for is the reference angle. So it's pretty clear. I could go back to the x-axis, and that would be a reference angle 4 pi over 5. But actually the shortest angle back to the x-axis is to the negative x-axis. Now hopefully you can see this pretty easily. If 4 pi over 5 gets me to here, and 5 pi over 5 is here, what's this difference? Pi over 5. If you want to do it mathematically, you would take 5 pi over 5 minus 4 pi over 5, and that difference is this reference angle. So the reference angle would be pi over 5. Just for fun, since we're doing this, what if my angle was 6 pi over 5? What would the reference angle be for this one? Well, first let me go figure out where 6 pi over 5 is. Well, if 5 pi over 5 is here, 6 pi over 5 is a little bit larger. So there's 6 pi over 5. So my reference angle, I don't want to go all the way back to the positive x-axis. I want to go here to the negative x-axis. And now you say 6 pi over 5 minus 5 pi over 5 gives this reference angle, which is going to be pi over 5. So what's interesting, with this example I just did, here are two angles, 4 pi over 5 angle and a 6 pi over 5 angle, and they actually have the same reference angle. So that can happen. As a matter of fact, I'm going to show you in this little talk how that actually becomes very important and very powerful in some things that we like to use in trig. But let me hold off on that. Let me do this last one. The last one says find the reference angle of a 15 pi over 7 angle. Now this one has an extra twist to it, and it actually goes back to some stuff we just learned about recently. We're going to have to use the principle of a coterminal angle because so once again, whenever I have a fraction here, what helps is if I can convert some of my information on my graph to have that same. So in other words, let me rewrite pi as 7 pi over 7. Now if I go all the way around, I've gone 2 pi radians. If I convert this to a denominator of 7, 2 pi is the same as 14 pi over 7. My angle is 15 pi. My angle is 15 pi over 7. So this goes back to actually this 15 pi over 7 angle is not in the unit circle. So I need to first find the coterminal angle. Remember what we do to find the coterminal angles? We start, when the angle's too large, we start subtracting 2 pi. So to find the coterminal angle, I'm going to take 15 pi over 7 and subtract 2 pi, which is 14 pi over 7. And it's actually pi over 7. So this angle is pi over 7, or we can think of it as 15 pi over 7. Pi over 7 is like this. 15 pi over 7, whoops, is like this. But they both end up at the same place. So the reference angle is going to be this. Hopefully, it's pretty obvious that the reference angle is just pi over 7. Now here is, let me just give you a brief little talk, explanation of the power of reference angles in trig. And later on, we will need to use reference angles, but for now, let me explain why reference angles really play a key role. We've been learning how to use the unit circle. So once again, the unit circle is all the special angles from 0 to 360 degrees, or from 0 to 2 pi radians. And once we know what our special angle is, we can go here to this point. This is the x and the y, and x is always the cosine of that angle, and y is always the sine. So once again, if someone says, if we need to know the sine of a 315-degree angle, we go find it here, and the sine is square root of 2 over 2. Whoops, the sine is negative square root of 2 over 2. Now, something you may have already noticed, and I may have mentioned it briefly before. Let's just look here. Let's look at degrees. 30-degree angle. What's the reference angle for a 30-degree angle? Well, obviously it's 30 degrees. Let me go over here. What's the reference angle for a 150-degree angle? Well, it would be 30 degrees also. As a matter of fact, if I keep going, let me look at the 210-degree angle. What's the reference angle for this 210-degree angle? 30 degrees. And finally, for this 330-degree angle, what's the reference angle? 30 degrees. As it turns out, these four angles, whether you're talking degrees or radians, all have the same reference angle. And the power of reference angles is that the trig functions, let me say it this way. If you have 2 or 3 or 4 angles and they all have the same reference angle, then the trig functions of those angles are going to be the same, except for whether it's plus or minus, but the values are the same. So once again, I'll say it again, then I'll show you on this unit circle why that's true. So if you have 2 angles or 3 or 4 angles and they all have the same reference angle, if I go look at the trig functions of those 4 different angles, the values of the trig functions will be the same, with the only difference being the plus or minus. Some of them might be plus and some minus, but the actual numbers are the same. And you can see it here. Look at the 30-degree or the power of a 6 angle. The cosine is square root of 3 over 2. The sine is 1/2. So those are 2 of the trig functions for this angle. If I go over here, this 150-degree angle has the same reference angle as this 30-degree. If 2 angles have the same reference angle, what do we know about the trig functions? They're going to be the same. And look, cosine of 30 degrees is square root of 3 over 2. What's the cosine of 150 degrees? The number is square root of 3 over 2. The difference is it's negative because now this angle is in the second quadrant and we know the cosine has to be negative. But the numbers are the same. For this 30-degree angle, what's the sine? It's 1/2. What's the sine of a 150-degree angle? It's 1/2. This happens because the reference angles are the same. Matter of fact, if I sort of combine these 4 angles all have the same reference angle, and if you look, the trig functions, the numbers are all the same. Square root of 3 over 2, square root of 3 over 2, square root of 3 over 2, square root of 3 over 2. 1/2, 1/2, 1/2, 1/2. The only differences are the plus and the minus, and that gets determined by which quadrant we're in. So for instance, over here, both these are negative because we're in the third quadrant. And the cosine and the sine are negative in the third quadrant, but the values are the same. And just out of interest, this next special angle, maybe we'll talk about radians now. Power over 4, the reference angle for power over 4 is power over 4. What's the reference angle for 3 power over 4? It's also power over 4. What's the reference angle for 5 power over 4? It's power over 4. What's the reference angle for 7 power over 4? It's power over 4. You know what? These 4 angles, these 4 special angles, all have the same reference angle. And what does that mean? the trig functions for those four angles are going to have the same numbers. And look, square root 2 over 2, square root 2 over 2. So look at the cosine. Square root 2 over 2, square root 2 over 2 with a negative, square root 2 over 2 with a negative, square root 2 over 2. Look at the sine of these four angles. Square root 2 over 2, square root 2 over 2, negative square root 2 over 2, negative square root 2 over 2. The cosine and the sines have the same values because these four angles all have the same reference angle. And then obviously this last special angle, pi over 3. The reference angle for pi over 3 is pi over 3. The reference angle for 2 pi over 3 is pi over 3. 4 pi over 3, 5 pi over 3. These four angles all have the same reference angle. And that's why when we look at this unit circle, when we're at, and it's interesting how with radians, you notice these four angles all have the denominator of 3. Turns out they all have the same reference angle. So they all have the same values for cosine and sine. The middle special angle in radians, you notice all have the denominator of 4. Those all have the same reference angle, and you notice the cosine and sine are all the same numbers. And finally, the reference angle here, you notice the denominator 6, pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. All the angles with the 6 in the denominator, they all have the same reference angle. Therefore, the values of the trig functions are all the same. So reference angles become a very powerful thing. And reference angles really are the whole reason why we can create this unit circle and why we can use it.